Welcome to topic 8.4, Electric Fields of Charge Distributions, daily video number 2. In this video, we will use calculus to derive the electric field of a point along the axis of a ring of charge. My name is Easton Landry, and I work at the Kinder High School for the Performing and Visual Arts in Houston, Texas. So before we jump into this next one, let's do a brief review on that problem-solving process we talked about last video. In particular, we want to start by drawing our differential element, whatever that might be, depending on the geometry. Then writing out our density equation in terms of that differential element, substituting known terms, factoring out constants, writing bounds, and integrating. Again, the ones that are bold are generally things we tend to get points for, with integrating, of course, being giving the point, but that tends to take the most time. Well, here's the small amendment. We are now, before we start subbing things in, going to look for symmetry. Why? Because oftentimes symmetry simplifies the problems for us and makes it easier for us to solve it without having to do all the other fancy things that you might have to do if you weren't looking for symmetry. You can still solve it that way, it's just a lot harder. So let's look at a particular example. This one here, we have a point P along this ring of charge as a charge of negative Q, some radius R, a distance of X away. This is the side view. If we look at it dead down the center, we're going to see something that looks kind of like this. So it's not actually located at the center. It is off to the side, but from that view, all intents and purposes, is located on the exact axis of that ring. So to set this up, I want to draw my tiny little differential charge element, dq, and it's going to have a thickness there of ds, standing for a little arc length. We'll explore that more throughout this video. We have this radius, which is again from our differential charge element to the point that we care about. And then we have our r hat, which once again points from our charge in the direction away from the charge along the radius. So it's just a unit vector of length 1 along the radius. Well, if we locate this to the other side, remember that because this was a negative ring, our dE is going to point opposite of r hat, which is exactly what we would expect. So we have our equation from the equation sheet where we kind of make our general notes, but we have this dq that has all these different points going on, and we need to solve for those. How do we do that? In terms of its linear charge density. Well, the total ring has some length L in the total charge, but because we know it's a ring and it's very thin, it's going to have a circumference, or 2 pi r worth of length. That has to be the same as our dq, our tiny little bit of charge, over our tiny little bit of arc length, which is that ds term. If we manipulate this thing to solve for dq, we're getting primed and ready to plug this in, but not yet. We're just setting up. And the one other thing we need to do is recognize that there's a big old triangle here that helps relate a couple of terms. In particular, that r, or little r in our case, is equal to x squared plus r squared, because that's Pythagorean theorem. And we take the square root of that to help find r. We're going to save these two equations for later, mainly because we're on a slideshow. If you're doing this on paper, this would all be one nice, happy, flowing document, but alas. So jumping back to this one, let's resolve some vectors. We have dE that's down here in the center of our setup. And I end up having two differential elements. I have this x component and this y component of that electric field. Using unit vector notation, the magnitude of xi I hat plus the magnitude of y j hat, those two add together to equal our total vector. Well, if I was doing this, I would then have to find the integral of all the i's, the integral of all the y or j hats, I hats, and j hats to hopefully make the whole thing come together. But symmetry to the rescue, because each of these elements that's pulling towards the ring has an opposite one that's going to cancel it out. I'm saying the y or the j hat direction, but ultimately these are the things that are perpendicular to our axis. They're all going to cancel. And how wonderful is that? So because they cancel, it's going to mean that we don't have to worry about those y components. Hooray! So this whole term we can ignore. And so we're really just taking the sum of all the x elements, all these elements that are pulling there to the left. If I summed those, I would find the total electric field. To help us with this, we're going to look at similar triangles. I have this little triangle down here, and I also have this bigger triangle of the whole setup where I can say that x is to dE as my x component is to r. Manipulating that thing around to solve for dx so we can sub it in later, we get something that looks like that. So here we go. We have a few things that we have from before, and let's sub this ratio into that equation to get this. Looks pretty happy. Things are going well so far. And we have our differential element that we know is basically like Coulomb's law, but with this del dq that's hanging out in there. So remembering that, just kind of compare these two, this is the vector that's pointing along r hat. This is the magnitude, so that r hat ends up going away. So if we plug this term in, what do we get? We get something that looks like this for our electric field, which might be more if you've been solving these a lot, where you're used to kind of starting somewhere in this area. Well, before we get too carried away, let's combine some like terms, and you probably know where we're going next. Remember those things that we saved from earlier? Let's bring them on back. So there they are. We have our DQ element we're going to be plugging in there. We have our R element that we're going to be plugging in for R. And when we put this whole thing together, it looks like a big mess, but all of these things, it's kind of crazy. The X, the Q, the R squared, all that stuff is just constants. I know it seems crazy, but every single DQ is the exact same distance away from that individual point. That's pretty cool. I enjoyed solving that bit. So then we go here. And if we set up our bounds to integrate, remember, we're taking not just this one element, we're going all the way from 0 to 2 pi r. That is the bounds of our integration as we go all the way around this loop. So doing that, we sub in our bounds, final minus initial. And this next slide, or not next slide, but we cancel those two things out. And then this next slide, kind of bumping everything up to see it all in one place, is the same as we had on the previous slide. It ends up turning into something that looks like this. And ultimately, that is our answer. Notice, if we're very specific with our vectors as we go through with our I-hat, this negative popped up when we sub that Q in. So we end up getting a negative I-hat. Sure enough, this is going to point to the left. You could have known that just conceptually from solving the problem or from looking at the system and saying, hey, it's all going to pull that direction. But again, if you hold true to the vectors, it does help tell you the truth by the time you get to the end. So what should we take away from this particular problem? Well, or for problems in general, be very intentional with your drawing. It's hard to know what you're solving for if you don't know what you're solving for. So drawing a really good picture with like clear DQs and DSs or whatever your differential elements are can help you visualize that better. Make sure you make it big enough to follow, as I say there, and proper labels. If you just say, hey, here's Q, but it's really DQ, that can help maybe lead astray. Similar, if you say little r, but you meant big R, or X when you meant, I don't know, X squared plus Y squared, whatever it might be, being specific is really important. And so anytime you practice to kind of reinforce that, make sure you're following a procedure. If I may recommend, a procedure kind of like this that we just practiced when we went through the video. Again, anything that you end up doing works, but this kind of process typically follows the process that gives you points on the exam. With that, thank you for watching this video and look forward to seeing you at the next one.